Okay, so this is about antimatter. So matter matters, but some matter antimatters. So in 1928, physicist Paul Dirac wrote an equation that combined the quantum theory and the special relativity theory. And he used that to describe the motion of an electron at a relative speed. This equation later won him the Nobel Prize in 1933. So the equation is basically asking, like, it's meant to give two different solutions where one solution would be about how an electron can have positive energy and another would have negative energy. But you might be thinking that's impossible because you can't have negative energy or two different signs of energy. So Dirac states that the equation explicitly that for every particle that exists, there's like a corresponding antimatter particle that's the same particle in like composition and everything, but it would have the opposite charge. So for like atomic molecules like the proton and the electron over here, who actually have the antiproton, which have negative energy, and a positron, which have positive energy, it'd still have the same placement, but just again negative energy. So if matter were to come in contact with antimatter, it would collide, and then both the antimatter and the matter would delete itself and just create some energy. And depending on the amount that goes into the process, there would be a lot more energy. So weird thing about this is that, so we all know how the Big Bang started. There's antimatter and matter collided and Big Bang happened. But this is odd since for that to happen, there would have been equal parts of matter and antimatter. However, there's obviously a lot more matter now after the Big Bang. So that would mean that in the beginning, there would be a lot more matter. There would be antimatter when they collided. So since antimatter is like really hard to find, something must have either added more matter into the universe or removed antimatter. So during the Big Bang, the universe had particle and antimatter pairs existing and ceasing to exist and creating energy over and over and over. But since the universe is not 100% energy, there must have been a small portion of matter that survived, and we see this in particle accelerators. In the particle physics experiments, we've been shown that the laws of nature do not really apply to the interactions of matter and antimatter. We don't really seem to know why, but there are many researchers trying to find out why and ongoing experiments as to see what is going on. So the antiproton decelerator. The antiproton decelerator is a machine that produces low energy antiprotons and slows the antiprotons down so that they can actually be studied. So what it does, it produces antiproton beams that are sent to different experiments that help the studying of said antiprotons. They're produced from a proton synchrotron, and it's fired into a block of metal, and it produces antiprotons among other particles. So the antiprotons have too much energy to create any like anti-atom. So the antiprotons are stored into the antiproton decelerator, where electric fields would attempt to slow down the antiprotons so that they can again be studied. It's kind of like a way of cooling it down because it's like reducing the amount of energy that the antiproton has by slowing it down. So what do we know about antimatter? We know very little. CERN is like the only place where antimatter is actually being produced, but there have been like ongoing experiments. They've been able to like store antimatter for more than a year with their collaboration with BASE. So since they're able to like store it, they will be able to start to move it and transport it all over the place so they can be studied in different areas of the world. So this leads to like uncover like difference between the antimatter and regular matter after creating a transportable antiproton trap. And that is it.